Welcome back, ladies and gentlemen, to another installment of Electric Current. We're going to take a closer look today at resistance. So let's see what that looks like. All right, if you'll remember, thanks to our good friend
Georg Ohm, in the 1800s, he found that when he applied a variety of potential differences to an electric circuit, and graphed that data, he found this right here, He got a straight line graph, which means that there's something about the material that was staying constant, because remember when we have a graph, it's got a constant slope, all right? And in this case, right, if we graph this, with current on the y-axis and voltage on the x, we could see that the slope, I over v, that's a constant. And in this case, that's going to be equal to 1 over the resistance. So depending on what you graph, voltage versus current, or current versus voltage, you'll have the slope equal the resistance or 1 over the resistance. But at any rate, we found that there are certain materials that behave this way. And that property, that stays constant, we're going to call that resistance. Now, it is worth noting that Ohm's law is not universal. In other words, it doesn't apply to all materials. We talked earlier about this. Materials that make a straight line graph on current versus voltage, we're going to call those ohmic materials. Obeys Ohm's law. But there are other materials like diodes, light bulbs, and such. They do not obey Ohm's law. They're going to make a different shaped graph. It could be like this, right, or it could be like that. Those are going to be non-ohmic materials. Let's go back to the electric circuit that we had discussed at the end of last lesson. This is just a TV plugged into the wall. All right, now when you plug into a wall, remember that you have AC. The symbol for AC is actually looks different than the symbol for a battery. So when you're supplying AC to a circuit, the symbol for AC is like that, right? A little sine wave, because remember that the charges go back and forth, creating an alternating current. All right, so that for AC, maybe we can write that next to it. AC. All right. The electrical load, right? The TV, the microwave. It's going to act as a resistance in the circuit, and we have two ways of modeling this mentally. One is in the water analogy. We can think of resistance as a constriction, right? So here's your pipe, and then you have a constriction, right? A narrowing, where it's going to be more difficult for flow to occur. The current's going to be constricted. So that's a way of modeling resistance in the water analogy. And then in the coal mine analogy, we have resistance being the power plant, because resistance is where the energy is used, right? It's where it's dissipated, right? So maybe use arrows, right? Energy given off as light, in a light bulb, or heat, all electrical circuits. So we can think of resistance as the power plant, where the energy is actually used in the circuit. On the right here, you see a symbol of, or pictures of some actual resistors. If you've ever looked at a circuit board, you might have seen something like this. So here are actually resistors in a circuit board. And then here are individual resistors all lined up next to each other. Notice that you see little bands of color on there, and those bands of color actually are a code, and they tell you what kinds of resistance each one offers. So like 1 ohm or 1,000 ohms or 10,000 ohms. Each color represents a certain number. It turns out that the resistance of a particular material is affected by several different factors. If we go to the next page, I can show you those factors. You see the 4 here: length, cross-sectional area, temperature, and material. To understand how each of these variables affects resistance, it's helpful to have an accurate model of current flow through a circuit. So I've tried to illustrate that here in the middle. All right, we have an electron, a single electron right here. That's our electron. And the arrows represent the motion of the electron through the wire. Remember that the drift velocity, the actual progress, that a charge makes through the wire, is only on the order of 1 meter an hour, right? So it makes very slow progress moving to the right, but that's because it's constantly colliding, with atoms in the wire, and that's why you see the arrows all over the place. It's definitely over time going to move to the right, but very slow progress, and often it gets knocked backwards on the way. Okay, so if you picture those collisions happening in the wire, you're going to get an idea of how resistance depends on each of these different factors. So the first thing, length, right? Obviously, the longer the wire is, okay, the more collisions there are, okay? And the more collisions there are, the more resistance there will be, right? So if you think of the charge as having a lot of collisions, obviously a longer wire is going to be more collisions, okay? The second factor, cross-sectional area, is basically like how fat the pipe is, okay? A fatter pipe is going to be more flow, right? And a thinner pipe, okay, is going to be less flow. I've taken this is right here, okay, this would be called the cross-sectional area. And I've blown that up here so you're looking at it head-on. And in this head-on view, okay, the green dots represent copper atoms. Now remember that these copper atoms are actually they're actually they're actually vibrating in place, right? So I can sort of simulate the vibration here like this, right? Each of the atoms is doing that. And so that's going to make for collisions, right? So notice that there's still a lot of empty space, okay, but the electrons are going to hit those copper atoms with a greater frequency. Or not a greater frequency, but a certain frequency, okay? So obviously the bigger the pipe, okay, the better the flow, okay? That's just like going back to the water analogy, okay? So we'll say bigger pipes, right, in parentheses as in thicker wires, okay, equals more current, okay, more flow. All right, the third variable, temperature, okay, remember temperature is a measure of the average kinetic energy of a material's molecules, okay, so as this wire heats up, what you're going to see is you're going to see atoms that are going to vibrate more energetically, right? If they vibrate more energetically, they're going to take up more of that space, okay? And so it turns out that a higher temperature, okay, I can write that very compactly like this, so as the temperature goes up, the resistance is going to go up because those atoms are going to be moving around more, and it's going to create more collisions between the charges, the electrons moving through the wire, and the atoms of the copper wire, okay? And then finally, we have the material itself, okay? Different materials have a higher or lower inherent resistance, okay? You can think of it almost like a material's natural talent for resistance or conductivity. So and we're going to call that natural talent, we're going to call that resistivity, okay? It's sort of the natural talent of the material to resist or conduct current, okay? So for conductors, right, we want that resistivity to be very low. We want its conductivity to be high. Okay, and so for conductors, you're going to see very low numbers, like on the order of 1 times 10 to the negative 7. Okay, table quick of some resistivities. Okay, let me pull that up. Let's see, where is it? Right there. Okay, and you can see that the materials that we know to be good conductors, silver, copper, gold, okay, they're at the very top of the resistivity list, but if you look at the numbers, they have the lowest resistivities, right? This table goes from lowest resistivity to highest resistivity, which we could also say as highest conductivity down to lowest conductivity. But take a look at the numbers, okay? They're quite low, on the order of a 10 millionth, all right? Okay, we'll go back to our screen here. And the cool thing is that we can actually put all of this together, okay? All of these factors can go together into an equation, all right? And let me write that out for you, okay? So we can calculate the resistance of a wire, okay, if we take into account its resistivity, which is going to be the Greek letter rho, okay, looks kind of like a fat P. The length of the wire, okay, the length of the wire. Let me clean that up a little. And we're going to divide that by the cross-sectional area, okay? So the way that we say this relationship in words, okay, is we would say that the resistance of a material is directly proportional to its resistivity and its length. In other words, if I double the length, I double the resistance. If I double the resistivity, I double the resistance. But inversely proportional to the cross-sectional area. Okay, in other words, the bigger the cross-sectional area, right, the more room there is, so the less the resistance would be. So that's the relationship that's we're going to use, okay, in some problem solving. All right, the last thing I want to look at is how we can use resistance in everyday applications, how we manipulate resistance to get what we want. All right, so let's go to the next screen.
And you'll see here, okay, an example of each of the variables that affects resistance manipulated for maximum effect. So let's take a look at length, okay. With length, we can vary the length of a wire to get more or less resistance, okay, and that's exactly what a volume knob is, or a dimmer switch on a light, okay. It's basically, if you want more sound, you need more current, okay. So louder equals more current, right? And if you want more current, you're going to need less resistance, right? So you're going to make that wire shorter. The louder it is, the shorter it is. Okay, so, and the same thing goes for brightness, right? If you want a brighter light, then you're going to turn down the resistance, which means just make the current go through a shorter part of the wire. Okay, microphones also work this way. They have a material, okay, so if this is the microphone, they have this granular carbon material, okay, and when you speak more loudly, there's this flexible diaphragm at the top, okay, when you speak more loudly, that diaphragm presses down into that carbon material, and it makes that part shorter there, which means less resistance, like a shorter wire, okay. All right, the second thing you can manipulate is cross-sectional area, okay. And that's basically just the thickness of the wire. If you go to Home Depot or a similar hardware store, you're going to see that wires come in different gauges. The only interesting thing about that, or one interesting thing about that, is that a lower gauge, okay, is going to actually be a thicker wire. And you're going to want different thicknesses of wire depending on the current you're carrying. For example, the wire that runs into your house, right, from the electrical grid, from the street, okay, at least at my house, and I have an average size house, a 30 amp rated wire, okay, it's going to carry 30 amps of current. That's going to be a pretty thick wire compared to, like, say, the wires we use in the classroom, right? The wires we use in the classroom, they're barely going to carry an amp. All right, another thing we can manipulate, right, is temperature, okay, and we talked about this already. Certain materials, if you cool them down enough, right, what's going to happen is the molecules are going to move less, and that's going to be less resistance, okay? And there's a separate equation that relates temperature to resistance. We're not going to deal with that, but basically as temperature goes down, the resistance goes down. And for certain special materials, right, you actually get zero resistance at that critical temperature if you get it cold enough. All right, the last thing we want to talk about here is the resistivity and how manipulating resistivity can also have certain effects. So we can take your human body as an example, okay? Every object, if you apply enough voltage to an object, it'll conduct, okay? So your body, typically, the human body has a very high resistance, okay, 500,000 ohms. But if you get wet, right, or sweat especially, your resistance can drop to as low as 100. Now that's a huge difference, okay? You can become very much more conductive when you're sweaty than if you're not. Okay, and that's because when you sweat, salt comes out, right, of your body, and salt equals ions, and ions equals charges. And there you go. If you move those charges, you have a current. I do want to talk briefly about the different kinds of current and what their effects are on your body. Okay, 0.01 amps, right, which is 10 milliamps. Okay, that's going to produce a tingling in your body. Nothing dangerous, but just a tingling sensation. Like if some people have taken a 9-volt battery, right, that rectangular looking battery, and touch their tongue to both ends, you're going to feel the tingling in your tongue. That's on the order of 10 milliamps. Okay, 70 milliamps. Now you're getting on what I'm going to say the heart current level. Okay, the level of current that your body uses to regulate its various systems, right? So that's going to start to get into the danger zone, okay? Twice that can be fatal, right? So 150 milliamps can be fatal. And obviously if 150 milliamps can be fatal, okay, 10 times that, right, or not quite 10 times, 1 amp, which is a lot more, can be fatal as well, but you might be surprised to learn that it's a little bit less so. Okay, and here's the reason why. What they found is that 1 amp is so much current that it just basically like completely shuts your heart down instantly. It's almost like it freezes the heart in time. And then if you come along with one of those defibrillators, right, those things that you see on ER type shows all the time, right, where they put the plates to the chest and shock them. Okay, basically what they found is that a really big current sometimes shuts the body down so quickly and completely that
when you come along with a defibrillator, it just starts right back up where it left off. Okay? Whereas these smaller currents, right, they tend to work more insidiously. It's like they sort of sneak in there at the same level as the current of the human body, and they sort of mess up the rhythm of the heart. And that can actually end up being harder to revive a patient from.